So, hi, may I start? So the just want to let you know, homework 5 have been put on the blackboard, so you got more than 10 days to do it. You will be due on next Friday, not this one, but next Friday. And so it's hypothesis testing. You already have the tools that you need, but today we talk about a little bit about add-in and F-test in the Excel, so that we know all the details you need to do. Okay. So today the goal is let me finish this hypothesis testing and for the Excel part, and then we will continue on the ANOVA, and we will do the ANOVA 2 part. One is one-way ANOVA, the other is two-way ANOVA. We'll probably finish one-way ANOVA this class, and then what two-way ANOVA on Wednesday. Okay, so then we'll be then what we have starting next week will be the last topic, regression. So for hypothesis testing, I don't think I need to remind you because we have done so many. So I just go straight ahead to talk about Excel. Okay. So I think we have talked about the t-test. All right. So what is left is the f-test, and I'll do the add-in. Okay. So what's left is this f-test in Excel. Basically, you just tell them the two input of data there, then it will give you the p-value of the f-test. Okay. So let me actually work it out. Okay. In Excel, showing the f-test to you. So it's f-test. Okay. So let me save the file. Let me save it as testing in, and it will be 14th of November 2000. Yeah, it'd be nice to keep your voice down a little bit. So this f-test, so what we have is x1, x2. Okay. So we have two data. So to convince you this is right, I just use the same set of the data that I put it in the here. So I just have okay. So that would be okay. So that is the data that I have two set of data. So I want to do f-test, and so let us do it from the scratch, and then we'll do f-test. Okay. So this is data. Let me do the thing from the scratch. Okay. So how can we do this from scratch from f-test, right? F-test, if you recall, right? It's just f. It's just S1 over S2 square. Okay. Compare the sample variance. Okay. These are, let's call small f, right? This small f statistics will have follow a normal distribution with n1 minus 1 and n2 minus 2. Sorry, n2 minus 1 as the degree of freedom. Okay. So so let us do the first, we just count what's n1 and n2. Okay. N1 is just counting how many of them, just count. Okay. And I just count from A2 to A7. Okay. So that would be the formula there. Okay. So that is giving us the N1, and you do the same for the N2. Right. This is how you get the N2. Okay. And what is next is we need S1 square and S2 square, right? S1 square and S2 square. And S1 square is just STDEV, standard deviation, using the sample version. And it is just this for X1. Okay, sorry. It just, oh, this is 2, right? Let me check. That's 3. Okay, so this is the sample standard deviation. Okay, and you do the same for the standard deviation for sample 2. Okay, so we have these 2 samples here. Okay, and then we have the F test statistics. We just call F is fine. I think the F is fine. It's clear. F is just simply the rates of the 2, right? So I just take the S1 of S2, right? This is the F. So for this, we can do 3 type of tests, right? We can do the left test, right test, and 2-tail. So let's do the left first. P-value, left, okay? And we can do left and right. So the left is just very simple, just F this, okay? Take this value, okay? And then you take N1 minus 1, right? And then N2 minus 1, and then true, okay? So this will be the p-value if you do the left test, okay? Because it's a left-hand side. If you do the p-value of the right, with just 1 minus the left tail, right? Because that is how left and right is being defined, right? It's the right-hand side area, right? So that would be the fun, okay? And the last one will be 2-tail, right? P-value of 2, right? P-value would be 2 times of the minimum of the left and right, right? That is how we understand to do the left and right. Okay. So it will be 0.99547. Okay. And if you do, you can do the F dot test. Okay, you can do F dot test. Then it's very simple. You just input the 2 data, then you're done. Okay. Okay. Yeah, supposed to be same, but I guess there's some. Let's see, but why there's some issue here. Oh, sorry. It should be the variance. I put the standard deviation. So we are. Yeah. Sorry. So the variance, not the SD. Okay. So so it should give you the same result. That's how. This is the way you can do it directly, right? Or you can do the way we do here. You just do step by step. Okay. I want to see if you have any question before I go to Addin. I just go around to check if you're able to handle that in your laptop or your iPad, if that's okay. Just go around. If you have any problem, let me know. If that's okay, then you'll be fine. Okay. So that is how you would handle your work. Okay. So so next I will talk about Addin, because that is a quick way to do this. Okay. And that's probably you may be working on. Okay. So if there's any question, before we go to the other part. So then we will, if there's no question, then we'll do the A in. Is there any question? Not over, sorry. So we will do the that in, and there will be a the two, basically adding is handling the two tail. Okay, there will be t-test, 3 of the 2 t-tests, and also 1 for the variance. Okay, so let's do the t-test. Okay, t-test, and we'll do is it independent, independent and same variance. Okay, and same variance. So that was the data. Let's check out. I do the okay, exactly the same data there. Okay, so I did, that means I can simply copy here. Actually, copy that. Okay. So this will be the data I'm using. Okay, and I think last time I showed you how we do it using the Excel function. So what's doing here is I will do a add-in function to do it. Okay, so if your laptop is Mac, then still should be the same, but I just illustrate for it to the window, because you go to work, although you use Mac, many of you use Mac, but you go to work, most likely you get a Windows system. Okay, unlike at least now, I mean, still most of the business world still use the Windows system. Okay, so have to put up there. So use the data. Okay, you can see if you use the analytics, it should be somewhere here has some data, but it's not. So what we're going to do is do the file, go to file, go to option, and then go to add-in. And here you see the NS2 pack is inactive. So we have to activate that. Then we just go, okay, and then data analysis appear here, okay. And with similar technique, I mean, somewhat related, is doing the Mac, because I don't have Mac, so but I think we do it in the topic 1, so it shouldn't be an issue here. So what we do is data analysis, and you click in, that actually has we have T here, and also with F. Okay, so we have 3 T's and 1 F. Okay, so let's do the 2 sample assuming equal variance that we're going to do. Okay, okay, so it's just first to the last one. I don't know whether you can see, but we go to the very bottom, first to the last one. Okay, and click OK, and the same as it's very simple. We just input what is the sample 1 and sample 2, tell them the difference on the check, which is 0 in our case, and you tell them the data label, and they're done. This is very simple. So just basically just put column A, because that's what we have, right? For variable 1, column A, and this is, we could column B. This is what we have for the column B, and then the difference you propose is 0, okay? Because they set the mean, the difference is 0. And the labels is because the first row of label, so you have label in the first row. Alpha is what we said is 95% confidence, right? Because they give the critical values, okay? And you tap down the output range, okay? Please, output is like here, okay? D1, okay? And once you input all these things, okay? Just tell them the range A, range B. You say them the 0, and then you have a label. So everything there, I think it's already in your notes. Okay, and click OK. Okay, and just wait a bit. It should come out. For some reason, research responding, which is not surprising. Sometimes the Windows system is okay, it's come out anyway, surprisingly. Okay, anyway, this is the come out. Recover. Let me save it. Okay, so this is the outcome here. As you will see, it basically gives you everything you want, the t-stat, the p-value, and also two-tail t-value. Okay, so this is how you're able to, you can do this in a one click, then you are done. Okay, so we save you a lot of effort to calculate the DF, right? Degree of freedom, save you the hassle to calculate the pool variance. So the main thing is the pool variance, right? And this is coming from N1 plus N2 minus 1, right? So just to illustrate this is to you, right? This is just N1 plus N2 minus 2, right? If you still remember, okay? So this is how we calculate that, okay? And just remember how we calculate this guy. This guy is the average, the weighted average of two variance, right? The weights are the observation minus 1, right? So basically just this minus 1, right, times this guy, right, the variance plus N2 minus 1 times S2, right? And the overall thing is the numerator, because it's weighted average, divided by sum of the weights, which is degree of freedom. But anyway, just do it from scratch again, minus 2, okay? So this is what we have. So this is the two things that I think you should know, how you arrive at the rest. I think the t-stat is very simple, right? Just do it one more. I think the t-tail, I think there's not an issue. This is coming from, okay? It's coming from this guy, right? Minus this guy, right? Over a square root of the pooled variance over the observation, right? Plus the pooled variance over N2, right? So that is the formula there, right? Just to remind you why this is right? The formula there is x1 bar minus x2 bar over square root of sp square over n1 plus sp square over n2. Okay, so that's why we have a fraction and square root of the that thing. Okay, so that's how we arrived at equation. Okay, I hope that is okay. Is there any question for how to do the add-in? I think the rest, I think that's not an issue. But that is telling you that Excel can do it everything very easily. And the goal of what we go through for the past 2 weeks is trying to give you the idea how we arrive those data. Because when you go to work, you never going to show the formula to your boss, right? Just tell them, okay, this is a p-value, but you have to understand how each entry being arrived, right? If the boss asks you how you get this number, if this number makes sense, do you do the right formula, right? You need to know at least in principle how you get those, right? This is applied to all field in future when you do computer programming, we try to produce output, right? And you at least understand what is behind the black box, right? You probably not need to calculate, but you at least need to know what is the formula behind, right? Because you're not, if you just blindly apply the black box, then everyone can replace you, right? You don't have a competitive advantage, right? You are just same as all the others, right? You don't have any expertise if you just know blindly how to run the software, right? And probably you know now these days a lot of high-tech firm, the big tech company actually fire many data science, right? Because they just know how to run packages, right? If you are data engineer, which you can produce packages, then you still get employed. But if you just know how to run Excel, just know how to crack this add-in is not going to make a living. Okay, maybe you are unlucky, but and when you graduate, it's probably likely that just know how to pack the add-in is not going to get a job. Okay, but anyway, I don't want to go too far, but anyway, this is how you get this one. Okay, is there any question for this one? If no, then I quickly go to show you the other one. Okay, and try to create another copy. Okay, and we don't have a same variance of different variance. Okay. Different variance. Okay. I hope there's no problem for this one. Is there any problem? Okay. Now let me erase this, guys. Okay. And for this one, okay, the same thing here, but we just where's the data analysis? Okay. Let me make this add-in comes out again. Okay. And I will do the data analysis. And here, this time I will do unequal variance, the second to the last one. Okay, unequal variance. Okay. So again, the same thing, actually everything is same. Just so the first entry put column A, or second entry put column B. Okay. And you difference 0. You label there, you put the output. I just put in D2. Okay. And everything the same as the before. Okay. So I click OK. Apparently, today's window is not. This room is not really. And there, you need to restart to make it work. Okay, very surprising, but what can you say? Okay, so you can see that for unequal variance, okay, the good thing is this formula, right, give you the DF being 7, okay, and you do remember to calculate this guy is very complicated, right? If you remember the formula, if you look at the lecture notes, it will be something like this, right? It will be something vastly complicated, if I remember correctly. Yes. So this is the formula. Okay. And here is there. Okay. So basically, it's the way to calculate the DF is much simpler, and then everything comes out, and then I think the rest will be simple, right? Shouldn't be an issue for you, but you do notice this is some way to handle it in a quick manner. Okay, so maybe I try to prove this is the formula that we're using, okay, because that is usually the way that you would try to understand what's going on by actually do the formula, right? If you remember, the formula will be S1 over N1 square and S2 over S2 square over N2, and take the whole square. This is a numerator, right? And the denominator, okay, will be sum of two terms, which is S1 over N1 to the power and over N1 minus 1. Okay, this is the first term will be just related to the sample 1, and it will be with the sample 2 will be S2 over N2. Okay, and take to the square and over N2 minus 1. Okay, so this is the whole formula that you would see in the slide. Okay, I just copy that. Just the one I written down gives you 7.02. Okay, so I just put the formula test here. Okay, this is just the way we input, right? Just to remind you, this, right? It's just S1 square plus N1 plus S2 square over N2, right? Square. And this one, right, will be just S1 square over N1 square, 1 over N1 minus 1, right? And this guy, right, is just S2 square over N2 square, 1 minus N2 minus 1, right? So this is the way that we get this formula, 7, right? And and finally, probably want to show the T-stat, right? T-stat is just the formula. If you still recall, maybe I just write down in case we just x1 minus x2 and square root s1 square over n1 s2 square over n2. Okay, so it will be just x1 minus x2, okay, over square root of s1 over n1, okay, plus s2 square over n2. Okay, so that the second part is the denominator, right? So that would be give you this answer. Okay, so in case you not fully follow, this is just this guy, right? And this is just this guy. Okay, so I hope that's clear how you get these two entry. I think that's the most important two entry that you need to know for this one, right? And this is how you arrive your solution. Okay, is there any question? Is there a question? If no, then I quickly go to the. Is there any question? No. If no, then I quickly go to the third test. Okay. Which is the paired one. Okay. So I will use the unequal variance. Okay. Paired one. Okay. Second to the third one, and the data we have is similar, but we add 5 and okay. So I think we just copy. So it's a pair. Okay. So again, I delete this. So what I'm going to do the same, I just have to go to data analytics, which is disable again. So let me add in, do the add in again. Okay. So what we're going to do is to use the pair one. Okay. So go to data analysis and do a pair. So it's the first to the last. And then you put column A and then column B, right? And then the hypothesized difference is 0. You have label, you tell them the output is D2, D1, okay? Then once you're done, you click OK. Okay, just the same procedure, there's nothing new here. And again, it will be hanging, it's not going to work. I have to close it again and then open. There must be some reason why this Excel didn't work as intended. Must be some this one. Not working. Let me try it again. So what I'm doing is the pair the one, and I put input A and input 2, and then 0, and then your variable. You tell them what output at D2, D1, and then we're done. Supposed to be, let's wait a little bit. It's not coming out, but I guess shouldn't be an issue. I think it's okay. We just we probably based on, you just can try it at home. I think it's already here. This is the output, and you give you the standard way we have done. So I'm not going to do it because I think Excel has issue with, but I guess it shouldn't be an issue for you. And you can do the same for F test. Okay, so the same, you put the entry there. You have the two data set. Okay, you put in the data there, then you give you the F test, the same. Okay, so I guess it shouldn't be an issue for you. I guess up to now you have enough expertise to handle the add-in, which I think the slides already very detailed how you can do it. Okay, I'm sorry I can't solve it because the Excel issue. I don't want to waste time on trying again. If you have a question, during the break you can ask me. I can work with you in your computer, but this computer doesn't really work. Maybe we can go to the dark classroom, the ELB, then we can solve it again. But for the moment, we just, I guess it's good to end our analysis hypothesis testing here. And before we go to ANOVA, is there any question? Is there a question about ANOVA? Sorry, hypothesis testing. If no, then we start ANOVA. Okay. I think it's more fun of ANOVA. So, and for ANOVA, is the topic here is ANOVA is actually coming from the ANOVA. So that's why it's called ANOVA. Okay. And ANOVA is the tool that have been very classical, and it is still used in business world, some social science, psychology, and science experiment. ANOVA is still a very good engineering the way to do it. Okay, and if you go to modern applied statistics, ANOVA is no longer emphasized. It is because it is a special case for regression. Okay, which you will see in the next week. We'll talk about regression, but we still talk about that because it's easy, for pedagogical reason, because this is easier to understand what's going on. And later, but we don't talk about in this class. But if you ever study the next version of this class, right, which is 2021, and they talk about regression, then you will later see this ANOVA is a special case of the regression is more, we focus in our class, we only focus on single variable regression. Look at how one variable with the other. If you allow yourself to generalize this to what we call multiple regression with multiple explanatory variable, in that case, ANOVA is special case. But let us consider ANOVA first. Okay. But what is ANOVA? And basically, it's just simply a t-test, okay, an idea. But t-test of two sample t's we just seen is comparing the difference of mean between two groups. Right? If you remember what is ANOVA, the basic thing is basically a what we do the add-in is a t-test equivariance. Okay, so basically is the ANOVA, the model is exactly very similar to this one. Okay, so this is the case where we have two normal, two bell curve, and they're the same variance. We want to compare the mean. Are the mean the same or different? Okay, we just see the grouping, whether they are boys or girls, old or young, right? You only compare and contrast between two groups. So ANOVA is trying to extend this idea from two groups to any arbitrary groups. What do you mean by that? And for example, in our school, right, if you want to see whether different college have different culture or different GPA or whatever measure you want to measure, and it's a college base, then you have more than two groups, right? You have more than two groups, and you want to see if multiple groups, do they different, right? Do you expect maybe people from Chongqing College, are they more religious than others, right? Or the people from Seoul College, is it going to be have more whole life than others, right? Because they're more remote, might be, right? And there are many things we can see, right? But you can see there's a lot of grouping. Like you don't want to compare young and old, right? Just very simple. But you want to compare different age group, right? Is it youth? Is it going to be the adult? Is it adolescent? Is it going to be child? Is it going to be kid? And so on and so forth, right? There are different type of grouping that is more than two. Then ANOVA is trying to see under the assumption of equal variance, okay, which is important. And we will see, do they have the same different mean, right? Just go back to the, maybe the whiteboard will be a good example of showing you the idea of such, right? So the idea of the t-test, right, just like your population 1, right? And there's some data there, right? And we assume that's normal, right? This follow this kind of distribution, right? I have sigma square here, and there's mu1 here, right? And there's another guy, population 2, right? And okay, and population 2, okay, there's a bunch of data, okay, and we assume this is following a bell curve, right? And this mu2, right? This is sigma here, right? So there's the two bell curve, right? The population is following a bell curve, okay? And our two sample test, right, is asking the question of, right, is asking this, right, is whether mu1 is equal to mu2. Well, this is what we have learned, right? Asking whether the same. Now, the generalization we do here is instead of 2, we can go one more. Actually, as many as you want. So we can have population 3, okay? And we have another one, okay, which is mu3, okay? We want to see if this, so on and so forth, okay? There are many grouping, as long as they have same variance, okay? In the population, we can just check if in this mean, the means, okay, of each group are the same or not, okay? So you want to see, say, for example, if you're a sales manager, you want to see different countries may have different sales, or if you're Hong Kong, you want to see if a sales of a certain all the store the same, right? Is it, say, for example, the easiest you can think is it Hong Kong Island, Kowloon Peninsula, and new territories have the same mean, right? Suppose look at the people's spending of 3 different areas and see if you want to put the store where you suppose you want to locate your new store, right? You want to check depending suppose you sell luxury good, right? Then you have to decide where to locate, right? Then you want to check if this 3 area, which area is better, right? Or you can even go to a street level. Which street you should locate your store, right? Then you have to many grouping to look at, right? Or Hong Kong, you have 18 districts, right? So you can see which district will be best to put in your store, right? So on and so forth. There are many issues you can put there. Okay, then compare group is very important. And historically, this is the ANOVA is the way that how people do experiment and test the efficacy of certain program or certain policy or certain business plan, right? Suppose you want to see in old day where they want to, for the farmer, right? They try to see different combination of sunshine, different combination of water, different combination of fertilizer, different combination of this and that, and what we call treatment, right? Different treatment and see if they all make difference or not, right? And the first thing to do is to do ANOVA. Okay, so you can see is the first one to single to do, right? Because you may have many treatment to do, right? And you want to see they're all the same or not. This is the first step, right? Once you figure out they're different, then you can do t-test or do many things. But ANOVA is the first round to check out if doing different things will be different, right? That's like the medical test, right? Or medicine. Then you want to see you have a new drug, and you want to see if this new drug, how to, you know it's effective, but you don't know how to fine-tune the dosage, right? Then you would separate patients in multiple groups, right? And then you try to put different dosage in different groups, right? And see they're different or not. If they're no different, then probably you want to use the lowest one, right? And so on and so forth. Right? So that is the user rate, right? Just you need to compare the performance, which is the mean performance of different groups. Is that clear what we're doing? So we're just basically extending the 2 sample tests, t-test, to the case of more than 2 groups. Okay, and this is very crucial because this is how you evaluate the performance of certain treatment, certain program. If they say, if you are the department chair of the marketing, right, the marketing division, and then you want to see if different channel is going to make a difference, right? Whether online, offline is different, or you want to see if advertising or campaign one, or you want to advertise in Twitter, Facebook, or YouTube, or TikTok, right? There are many different channels, or go to the bus or MTR or whatever. There are many things you can compare, right? So that is the way we're looking at. Okay. So as I said, here I focus on one way today. Tomorrow I could focus on 2 way. So what's 1 way and 2 way? As we've seen, 1 way just like each observation will have one grouping, right? So just like you look at college, every individual would have a college affiliation, right? One student is CC College, one student ANA College, one student SAW College, so on and so forth. Each student have one unique group, okay? But however, many times you would have each observation would have more than one way of grouping, okay? A student can be categorized by college, okay? But can also be categorized by their gender, male or female, right? So male and female and college, right? Or if you want, you can compare college to their majors, right? You want to see if the majors and the college would make a difference, okay? That we will talk about this on Wednesday without 2 way ANOVA, okay? We just focus on 1 way ANOVA and see whether grouping would make a difference, okay? So the idea is very similar to what we have in the it's exactly two-tail t-test. Okay, it's a two sample t-test. Okay, so let's consider the following. So as I said, each observation has a grouping information, either your gender, your age group, or your country. Okay, and how do you describe it? It's usually sometimes they call factor. So we have observation, and also we know which group they're in. It's called a factor. Okay, so that's why when you collect information, you have n data point. Then you actually have not n data point only, with n pairs of data point. Each one you have is observation as data point. Say, for example, X1, G1 may be student number 1 if you care about, say, GPA, okay? X1 will be the student 1 GPA. Good one may be college of NA, okay? So this is what you have, right? So suppose you have like this, right? This is guy number 1, okay? And we know his GPA is X1. We know his college is NA, right? So GPA may be 3.3, okay? And girl number 2, okay? And what you know is his X2, which is his GPA may be 3.5, and his college may be CC, so on and so forth, okay? So for each individual, we have 2 information. One is the variable interest, which is maybe GPA, his spending, or time to go to party, or so on and so forth, right? Or traveling time to school, whatever you're interested in, okay? Which we have been doing this, right? But the only additional thing is G1, which is the grouping, okay? And we use the notation called C, okay? It's number of groups, okay? Number of C's group. So we have a C number of group. We have G1 is I use big G just characterize. Okay, you don't need to group 1 is the way I do generically, and group 1 can be referred to. Suppose college, maybe this is college of NA, this college of CC, this college of so on and so forth. Okay, so this is the this just a nominal variable. If you recall, have no. You put whatever symbol, doesn't really matter, just the name of it. Is that clear? So we have the numerical variable, okay, together with a nominal grouping, okay? So is that clear what the data we're working in, okay? Actually, before we had the same idea, right? Because before we have version of this, right? But the grouping doesn't exist, okay? Say, for example, if you go back to maybe it's good to see when we do this guy, okay? We have this data set, okay? This is already a already paired one, but the original data you should have is X and G will be 3, is group 1, okay? And 4, this one, right? Is group 2, so on and so forth. 7 will be group 1, sorry. Maybe I should use the bigger one, okay? G1, G1, and G1, okay? And then goes on to here, right? 3 will be G2, 2 will be G2, 3 will be G2, okay? The last one, okay? Is it clear? This usually data you have it like this form, right? That's how we collect data, right? You collect data and you have the grouping information, okay? Here is very nicely ordered, but when you collect data from scratch, usually it's different, right? And here is this is raw data. You put it in this form, you can analyze in Excel. Okay, so this is this also the usually data you store when you download from database. It's also like this, right? It's like you have each entry and tell you what is the grouping. Okay, is that okay? Because usually data doesn't come in this nice form. Very rarely you have this a very nice form for you. Okay, usually this is the format that you get from the data set. Okay, and actually there's a name there. Usually I don't talk about that, but usually this is called a long format. This is called Y format. Okay. And if you learn any data science package, R or Python or whatever, there's a conversion between the two, right? And for Excel, I don't think they have this process, but I think if you might be there, but I don't know. But at least for Python or R, other software package, they can easily convert from one way to the other. Okay, but we are not data scientist class, so basically, you don't need to worry about this. Okay, but you should know, you should able to see to transform this to this one. Okay, is that okay? Is that okay? I mean, of course, in Excel, the easiest thing to do is to use the filter function and copy and paste. So usually that might be okay, but anyway, is there a question? Okay, so this is the data format, but I don't want to go into details of it. Okay, so this is the data, and as I said, this is the data that you usually from a spreadsheet, the raw data from a spreadsheet. Okay, and the problem is this one is not super convenient to write. Okay, so this is how you would see the data in statistics formula. Okay, instead of saying x1 g1. Okay, let me finish this one, then we have a break. Sorry, xn gn. Okay, you would just grouping things together. Okay, so you have a data which we will have a group. This is the group number 1 up to C, and we have the second subscript is the number of observation, is I and J. Okay, J will be from 1 up to N I. Okay, of I don't know how to write NI, right? So each group will have NI number of observation. Okay, so let's see the Y format. Okay, so this is the format. So the data you have is, I said, you just grouping all the same data, same group would group in the column, right? This will be x11, x12, x1n. So what does that mean? If this NA, this is CC College, this is the first observation for NA. Okay, because this one means NA. Okay, and the second one means the first observation of NA College. Okay, and same, this is also an NA College. Okay, but this is the second observation up to N1 observation. Okay, and similarly, this is the first observation of CC College. Okay, and this is the last observation of CC College. Is that clear? How you read that is the first subscript is the group number. Okay, it's 1, 2, 3, 4 up to C, and we have the last digit. So last number in subscript is the number observation, and you can easily see that from this diagram. N1 need not equal to N2. Okay, it can be equal, but in general it's not equal, right? When they are all equal, usually they call this data is balanced data. It's called balanced. Usually they call balanced. And in this case, it is not the same, then it's called unbalanced. And in the one-way ANOVA, we allow unbalanced. Okay, we can do different thing, but when we work for the two-way ANOVA, we're working on the balanced one. Okay, so because of ANOVA is very complicated two-way, so that's why we focus on the easiest case. Okay, for one way we don't have any this kind of restriction. Okay, so maybe I have a break here of 10 minutes. Then we will continue our journey on one-way ANOVA after the break. Okay, so go around to see if you have any question. Okay, that's a 10 minutes break. Okay. So let us continue just to remind you what we're doing as ANOVA is we have data. Each data point is separated by group. Okay. And the notation you have is Xij, where the first one I refer to the grouping, the second one refer to the serial number in that group. Okay. And okay, so if we know this, then I guess we are almost ready to tell you the everything. Okay. So we will have a classical model, which means that everything follows the bell. Okay, we have the same sigma. Okay, so that is exactly we have here. Okay, each group have the same variance. Okay, and potentially we want to see they have different mean or not. Okay, so this is basically this the bell, right? Basically is ANOVA. So this graph is summarizing what is the set of ANOVA. Okay. So, and if you see some of the book, okay, they would go a little bit further, okay, and the other way to express this is each observation, okay, is given by the group mean, okay, plus an error term, okay. Why can we do that? Okay, it's because the idea is the following. It's very simple. Let me draw a diagram here, then you will see what we are talking about. Okay. Suppose this is the bell, right, of Xij, right? And you have the mean of, sorry, let me make it. This is mu I, right? The group is, because it's group I, right? So the mean is mu I, okay? So what actually is here is, what we write is the following. So this is 0, okay? And we move this bell here. Okay. And this becomes epsilon ij, okay? And we just move to the left, right? In this case, right? How much you move, it's just mu I, right? So that's why you can decompose it into two parts, right? Xij. One part is the constant part mu I. The other part is called, we call error term. It's called the green one, random errors. Is that clear? Is that clear? We have the bell in somewhere. We move it to 0, okay, by subtracting from its mean. Is that clear what we are trying to do? Okay. Is that okay? Now, with this, okay, we will define several things, what we call the grand mean, okay, the grand mean, or overall mean is mean of each group, okay, we'll give you the mu, okay, and the overall mean minus the grand mean is what we define as the treatment effect. Okay, why do we define this way? Okay, because you want to see, right? Say suppose this is the average GPA of the whole school, right? This mu, right? And mu I, suppose I is the group, is the college, CC college, right? You want to see the mean difference between the overall, the whole school minus the group mean of the CC college. What is that you get is the treatment effect, right? Is it being in CC? Is it a difference there? Right? So that is how you define this, right? Because mu of I, right, will be just mu minus epsilon I, right? So that's how we define the treatment. Right? So let me see the diagram. We don't have diagram here. So maybe I draw it. So let me draw another diagram here. Okay. Let me draw a diagram here. Okay. What do you mean by that? Suppose I group one. What color I use? I use blue color. Okay. I have blue color of this. Okay. And okay. And suppose this is x bar 1. Okay. And this is mu. This is mu 1. Okay. And maybe I use x1, not x bar 1, maybe easy. Okay. Because it will give us the same variance. Easier to see. Okay. This x bar. And I have also have another one, maybe here. Right. This is the mu2. Okay. And this is x2. Also have the same variance as you can see, right? And I also may have another one. Okay. Mu3, that's sigma here, x3. Okay. And maybe 0 is here. Let me draw 0 here. And of course, the way we define, right? We can always have the same variance. Okay. This is same for epsilon 1, right? Same as epsilon 2, epsilon 3 are the same, right? Because the error term is same for 3 cases, right? Because they're same variance. Okay. And we do have another thing, which is what we call the mu. Mu is what? Mu is just mu1 plus mu2 plus mu3 over 3. Okay. So basically just averaging these 3 mu. Okay. And what is the treatment effect here? The treatment effect here is this one is alpha 1, and this one is alpha 2, and this is alpha 3. So I hope this graph will give you the idea what we're actually doing, right? The thing is we want to see if mu1 equal to mu2 equal to mu3, but we can just say is alpha 1 equal to alpha 2 equal to alpha 3, 0. Okay, so let me write down here. Okay, the main idea is we want to, the null is mu1 equal to mu2 is equal to mu3, right? The grouping make a difference, or the same of asking is alpha 1 equal to alpha 2 equal to alpha 3 is 0. Okay, so that is the main idea here. Okay, is that clear what we are ANOVA is doing? Okay, we just transform everything is a bell. Okay, there. Okay, is that okay? I hope this is at least you would be clear at least from the diagram, right? What we are doing. I mean, is that okay? So later you will see this diagram. We will be using it, and this will be serving the basis of what we actually doing. Okay. So this diagram you will see again, and then this You understand why to do it we rely on F-test. Okay. So this is the so if you understand this, the group mean and the treatment effect, okay, then we can define what is the sample version. Okay, because gram means overall mean. So the sample version of it just looks like complicated object, but it really looks clumsy. But what it means is the two summation sign here, or looks very unintuitive. What it means is you just adding I as a group from group number 1 to group number C. So it's sum over all groups, right? It's group I from group C. The second one will be, this is holding each group, right? So for each group, right? Sum over all observation, right? Because you just keep doing the group I, you sum all the observations from 1 up to n I, right? So basically just very simple, just add all the observation over n, right? Just you discard the grouping information, calculate the average. That's it. Is that clear? Because this is, you disregard any about grouping, just average. Is that okay? Is it this one okay? The second one, I guess, is not something terrible. It's just I fix the group I, okay? I fix I sum, it's just sum all observations in group I, right? Because you just change the J from 1 up to NI, right? So basically add all the observations in group J, right? Group I. So basically just like the data, it's just like you pick up the college CC, for example, you average the GPA of the CC student, right? Or average GPA of the NA student, or average GPA of SOS student, right? So it's the average of the group. Is that clear? The first one is overall, okay? The second one is the group. Is that clear? Is that okay? So let me go back to the data, and you will see how. Is that okay? Is that okay? Is it done? Just wait one more minute. Is that clear what the notation means? Because it's good to know how you can read those carefully. Okay. And no question, then I would go back to the, maybe I just don't erase it in case you want to see. Okay. So how can you do the group? If you want to do the overall mean, it's just very simple. If you want to see, add everything up, okay, sum of them divided by n, right? Then this gives you the overall grand mean, right? This is the estimate of mu, right? And if you just pick this sum, right? Pick up this sum over n1, this is x bar 1, right? Just add this. The column average is the group average, right? So this is estimating mu1. Okay, so that is how you can visualize this from this diagram. Okay, I think it's easiest thing is to try to imagine how to connect your mind from the picture. You would understand what's going on in the notation. Of course, once you know it, then you know it's not a problem. But the first time you learn, it's better to visualize in the spreadsheet idea. And this is actually useful when you learn advanced statistics class, because the notation will be a lot when you actually go to there. Then it's always good to think about in terms of data and think about how to work it out. And when you actually have to deal with the data, then you know how to work it out. It's very important. And of course, I know many of you, this is the last class of statistics, but But at least you know that maybe you were doing a master program, you come back to this again, likely. And you know, most of the time now, everyone have to do master program sometime because of the way that it's very competitive labor market. So you may face it again. Okay. Anyway, if you don't do a master program, you will learn it some way or other. You will learn it by doing in the work anyway. And so as I said, their means. So that's why they are. I don't prove it, but they're unbiased estimator. Okay. If you want to estimate the grand mean in the population, then just do the X bar, right? If you want to estimate the group mean, then just use the sample group mean. Okay. I guess that's not a big issue here. Okay. So let's show you how you do the calculation. I'm not going to go to line by line, but as you can see from this, right, the grand mean is just the sample grand mean, right? Just adding everything there divided by 12. Okay. And for number, I'm sorry, for group 1, it just add 4 of them divided by 4. Okay. So I guess it's clear how we do X2 bar and X3 bar. Is that okay? I don't think I need to go line by line for this one, right? Because this is so trivial. Okay. And as I said, later you will see when the Excel add-in, everything comes out directly. Okay. So we don't actually happen ever, probably accept your assignment for once, you will just do this. Or otherwise, other than that, I mean, probably you just copy from Excel anyway, but I'm not sure you actually do it. But at least you see how in principle you arrive there. Okay. So that is the group mean. Okay. So I hope, I mean, you go back and check if you have any question about this group mean. And as I argue, we have to do is that all the group are the same or the treatment effect is 0. Okay. And I think I have already set the application. So I will try to show you how to do the F-test. Okay. So to test this hypothesis, whether the same 0 treatment effect or the same mean, group mean are the same, we will do F-test. Okay. So do note that if the C is 2, only 2 groups, okay, ANOVA, go back to the t-test you learned. Okay, so the result actually you can check later, you know how to do it from Excel, you actually can check the result you get from t-test if you're on 2 groups, same as F-test. Okay, but you have more than 2 groups, then F-test will use it. Okay. So now again, I'm sorry there's terminology because this is a lot of things to remember. Okay, at least to know what's going on. Okay, so what we are actually going to do, okay, is remember we're going to do it for an F-test. Okay, F-test means we are comparing variance. Okay, and how do we compare variance? Okay, and the main idea is before I go to here, maybe I may just do this one, and then I talk about the variance. Okay, but we need some notation first, so to see what's going on. Okay, so the first one, sum of squares. Oh, sorry, sum of squares. So sum of square, we have 3 terms: SST, SSG, and SSW, and then we'll tell you what do they mean, and then you will see why we do F-test. Okay. The first one probably is not something very surprising. Basically, just this, you have seen this in the grand mean. You're just adding each observation. Basically, disregard the grouping, right? Because just add them all. Okay. And in particular, what you do is you just calculate for each observations minus the grand mean, right? So it's the distance between each observation and the grand mean and square. Okay. And this we call total squared variation, right? So just look at each observation related to X bar. Okay. So that would be the first thing we get is what we call SST. Okay. Later you will see why we define that, but slowly we will just wait a little bit, 5 to 10 minutes, then we know why we are going to do that. The second one, you will see the difference is, again, you are just adding all observation, right? So actually the three of them actually go over all the observations. The difference is now we are not going to taking the difference between each observation and the grand mean, but look at the groups. Okay. Okay, each group, okay. And you replace the observation value by its group mean. Okay. So instead of looking at the raw data, you replace every observation by group mean. What does that mean? It means that there's no more variation within group, right? Because everything within the group is the same value. So basically, all the NA students, okay, will not have different value of GPA, but replaced by the average of NA student. Look at all the raw data of CC. You don't talk about the CC GPA for each one, but you replace them by average of the CC GPA. Okay, so what is it measuring? Later you will see is we're talking about the difference between colleges, not individual students. Okay, we're looking at because there's no individual difference among the students within the same college, same grouping. Okay, so that's why this is we are measuring the variation. That's why I call between group, right? There's no more within variation, right? No people within the same group actually share the same thing. Okay, so that's why it's called SSG. Okay, and here we do the other way around. Is instead of talking about the variation over the grand mean, but the group mean. Okay, so basically you're talking about how each student within the college are different from each other. Okay, and there are three variations, right? The first one total, the second one is within the group, the other is between the group. Okay, and turn out the math we don't prove is the important equation, which said 1, 2, 3 means 1 is equal to 2 plus 3. Okay, we are not going to prove it. The proof is rather it's not difficult, but we're not proving it, but we will show it you in the graph. Okay, so I just convince you this is right, but actually we need to prove it. You actually need to work out the math. Okay, the math is not difficult, but I don't think it's important for our class. Okay, because you never calculate it anyway. Okay, but you need to know this formula. Well, later you will see. Okay, let's go to this next slide and see what do you mean by that. Okay, so let's arbitrarily fix a data point here. Okay, so this is group 1, right? Let me. Okay, what the diagram? This is group 1 data. Okay, and I have another type of group 2 and group 3, but I'm not going to talk about those. Okay, so do note that this is not the mu but the x. Okay, so basically this is coming from data. Okay, and this is data, this is group mean. Okay, this is group sample mean, okay, of group 1, and this is data you get, right? And this is sample mean of group 2, and so on and so forth, right? And I don't know this color, right? This is the sample group mean, right? And we have overall mean is here. Overall mean, I don't know, black one, right? Overall mean is here, right? So let's pick up one particular observation from group 1. Okay, we pick, suppose this guy. Okay, if you calculate SST, right? Look at your slide. It's looking at this observation, the distance to the overall mean, right? So this is the distance from the observation to the center of overall data, right? It's a grand sample mean, right? And this is the SST, right? You square this guy and sum of every observation is SST, okay? And we try to decompose it, these two parts, right? We can decompose it into two separate parts. Okay? When you travel from each individual data to the center of data, okay? You can travel separated in two ways. First, you can travel to the mean of your group, okay? Which is called SSW, because you just care about within difference. This is, right? This is the first, okay? This is the third one, okay? And then you can go again, one more step, okay? It's called SSG. Okay, so that is how you can travel, right? Suppose you can imagine the following, right? So you can imagine the grand mean of the school is in the center of the CHK, right? Is the right at the real center. So how you get to the center of the school? Suppose you're NA college, right? You got NA college at many places. You go to the center of NA college, which is SSW. And from the center of any college, go to the center of the school. That is called the SST. Okay, so basically the following, right? So we have a CHK is very big, right? So this is the center of CHK. So if your NA is here, okay, you have one observation, you go to the center of NA, okay? So you can go here first at step 1, okay? And then you can go here, step 2, right? Or you can directly go there, okay? And it tells you that they're the same, okay? You can just go two-way. Is that clear? So the variation can be decomposed into two parts: the variation within group, the variation between group. Is that clear? Okay. So the key here, okay, is the following. You do notice that, okay, SSW comes from, the difference actually comes from, the variance is actually measuring sigma square, right? Because it's looking at this, is running around this group mean, right? That's what we assume, the bell curve, okay? And this is also measuring sigma square, right? Because it depends on what kind of you draw, right? It's also sigma square, right? It's a measurement of sigma square, right? Of course, you have to divide the thing to get appropriate measure. The thing is, if mu1 equal to mu2 equal to mu3, right? So these two ways of measuring sigma square should be the same, right? Because they should be, there's no difference, right? I mean, if there's no difference between mu1 and mu2 and mu3, they should be measuring sigma. If they are not, right, that means that the measurement, if they're actually different, right, this SSG will be way bigger than SSW. You try to measure, because if the actual difference, right, the difference between the mean and the group will be much larger, right? So that means that we are comparing the variance measured by this over this. Okay, later we'll write it out, but the idea is like, if the difference, this will be big, right? So that means that actually we're doing one-sided F test, the right-hand side. Okay, we'll go there, but that's the idea. Is that clear why we're doing this? It's because they were separate to each other. The SSG if you try to use SSG to measure the variance, okay, we're bigger than the SSW. Okay. So we will see how we use SSG and SSW to determine. But before we do, we go ahead. Ask any question? Okay. Any question? If no, then we just go to how we determine. Okay. SST. I mean, I'm not going to go to the math. Okay, but just try to see it is quickly. One is here. Okay. And one is here, so on and so forth, right? So every element you subtract from its grand mean 4, right? And get U70, okay? So I guess it's easier to, is that okay? I'm not going to do this one by one. Is that okay for this one? Okay, and I remind you that you never do this and in your real life, but because computer gives you everything like this. You just need to know what's SST. Okay, you never actually calculate this guy in any practice. Okay, but you need to know what's SST. Okay, and similarly, you can calculate SSG. Remember, SSG is you are trying to replace everything but the group. So you can see here, instead of 1, 2, 1, 1, 2, 4, what you do is you just erase them, become 2, 2, 2, 2. Okay, because that is Y2 is here. And similarly, you replace this guy by 5, 5, 5, 5, 5. And you do the same because they're same mean, you will 5, 5, 5, 5. Okay, so that's why you have all the 5 here. Okay, you're the 2 here. Okay, is that clear how you do SSG? Okay, just replace. I hope this example will be clear to tell you how in principle you can calculate. But as I said, you never do this, okay? You never do this in practice because Excel easily generate all this thing in a one click. So there's nothing you need to worry about the calculation. You just need to know, okay, what are they measuring? Okay. And the next is SSW, okay, which is what you do is you just subtract each one from the group mean. Okay. That's how you will see 5 is here. Okay, instead of 4. So that is the difference. Okay. So that's why I verify that you can check is SST equal to SSG plus SSW. As I said, we don't prove it. We show it the graph, right? The variation, total variation is going to be the variation within the group plus between the group. Okay. So don't go to the math, but this is the proof. But this is the proof you can see. I think I don't think I prove it here, but anyway. So here we want to define 3 different measures of sigma. Okay. So this is the first one is you measuring sigma square, right? Without thinking about the grouping, right? This is just basically sample variance, right? You forget about grouping, you add every single thing minus the overall grand mean, right? Basically, as maybe I write the English, right? You just try to, this is you estimate sigma without grouping, right? So basically forget about that group. Just add them up and divide by their mean, right? Minus the mean and square and then divide by Anderson, okay? So this is the raw thing we have, right? But we are not using this one, okay? Because this is something that we are not using, okay? Don't worry, we'll use the next 2 one. This between group. So this is basically the question is also estimating sigma. Estimate this one. But you relies on sample group mean. We don't group mean, we find group mean. So look at each group mean, how it's different from the overall mean, right? Just this is what it is, right? And probably you ask why C minus 1, right? But it's very easy to see because you have C groups, right? So, and minus 1 is just the way we do, right? We just have the minus 1 when you try to calculate that, okay? Is that clear? So that is how you because you fix the overall mean, then you have one less degree of freedom. That's what we said. But okay. And this is another way to measure sigma, right? Sigma squared. Here we have estimate, right? Sigma relies on variation, rely on difference within group, because you subtract it from the group, right? Group mean. You just forget basically looking at the mean of each group. Okay. So as we said, if mu1 equal to mu2, right? So that means that these two are the same, right? Because if mu1 equal to mu2 equal to mu3 mu_n, you expect these two guys the same, and hence they should give you the same measure, right? You use the F test, you can come to the same thing, right? Because they're same. There's no difference between using this and use that, right? X bar as X bar I, the same thing, right? And that's why you should expect under null, these two, the variation is the same. But turn out, it may not be the same, right? So is that okay? So I go to the last slide of this today, will be this one. So this is how you calculate. Sorry, I have one more slide. So MST and FWMG, good calculation. So just one very last slide is just this one. Okay, I'm not going to talk more because I think it's time. So we just compare MSG and MSW. Okay, and as I said, you would expect the MSG if the same, that's the same. Otherwise, this one is much larger because it also contains the difference between group, right? Because if that separate, MSG will have much bigger than within the thing. Okay, so I will talk about this in the next class. I'll actually implement this, but this is just F test. Okay, it's very simple. As you can see, will be just the difference. Okay, I'm not going to talk. So I see you on Wednesday. So this is very simple F test. Okay. Anyway, see you on Wednesday.